So in this video, we're going to determine a differential equation for the velocity v of t of a falling body of mass m if air resistance is directly proportional to the square of the instantaneous velocity. So in this problem, we assume that the downward direction is positive. So that's positive, and we use k is greater than 0. That means it's positive for the constant of proportionality. And obviously, we have g is greater than 0, which is 9.81 meters per second squared. And that is the acceleration due to gravity. So we'll write it first. So in this problem, we're required to find and to look for dv over dt. And we have these given parameters, which is m. Let's go define this first. This is the mass of the skydiver. And we also have g, acceleration due to gravity. And we have k, the constant of proportionality. And we have also v, which is the instantaneous velocity of the falling body with mass m. So these are the parameters we're going to use, and we're going to use this to look for dv over dt. So we expect our answer to be this one. Our dv over dt should be equal to g minus kv squared over m. So we've already defined these parameters here, g, k, v, and m. So in this problem, not only are we gonna go solve for dv over dt, which is basically the acceleration, because you remember that the acceleration is defined as the instantaneous change in velocity per instantaneous change in time, right? So that's denoted as a is equal to dv over dt. So not only are we gonna going to look for that one, but we're also going to look for the v of t. And not only that, I'm also going to introduce you with the terminal velocity. Terminal velocity is when the acceleration goes to 0. So when your falling body does not accelerate, that's when you reach terminal velocity, when your acceleration goes to 0. That means the forces that acting on the body actually equals. So I'm going to talk about that later. I'm going to solve for first dv over dt, and next is I'm going to go solve for v of t using this dv over dt equation here. And I'm going to introduce you with the terminal velocity also, because we're going to express our v of t also in terms of terminal velocity. So step one, we're going to identify the forces acting on the body. So we're going to draw like the free body diagram. We're going to go draw it. So say this is our object, this is our object, and the forces acting on that object or on that body is just the F of G, the gravitational force, which is equal to mg. So as you can notice here, it's defined here. That's mg. That's the force done by gravity. And we also have an upward force. And this one here is the air resistance, which is equal to, or we just say F drag. We say F drag. It is the dragging force or the air resistance, which is directly proportional to the square of velocity. So we're gonna go put a negative sign here because your direction is pointing upward. As we said before, that we're treating the downward direction positive. So this one here, the dragging force or the air resistance, should have a negative sign. So now we've already drawn the free body diagram of our object. So that means we've already have the forces. We've already drawn the forces that act on the body. We have F of G, the gravitational force, which is equal to mg, and we also have the dragging force or the air resistance, which is directly proportional to the square of the velocity. So I'm going to talk about first, because in other problems, we have either linear drag force and we also have quadratic drag force. So in this case, we have a quadratic drag force. And the difference between the two is the linear drag force occurs, this kind of air resistance occurs when the object is traveling at low speeds. So examples would be objects falling and moving at low speeds like dust particles, or in air, or objects moving through like highly viscous fluids. In linear air resistance, the airflow around the object is mostly laminar. So laminar meaning smooth and in order. But in quadratic drag force, this dominates in high speeds. High speeds including skydiving, airplanes, or fast moving sports balls. So these we use a quadratic drag force. Or simply when the airflow becomes turbulent. Turbulent meaning it's chaotic. Laminar it's just steady. It's smooth, it's in order. But turbulent is just chaotic. So I'm going to show you a picture of laminar flow and a turbulent flow. So this is a laminar flow. It's smooth. It's in order. It just goes in parallel. See? But in turbulent flow, this is how the fluid moves, or this is how the air moves. The airflow is so chaotic. It's not linear, right? It's not smooth. It's not in pointing in one direction. It's chaotic. So those are the difference. So that's the difference between linear drag force and quadratic drag force. So you remember laminar, you use linear drag force, and linear drag force, we use F drag is equal to negative BV. That is, so the dragging force is directly proportional to V. But when in quadratic, that's why it's called quadratic, because we use negative kv squared, which is the dragging force is directly proportional to the square of the velocity. So now that you know, we're gonna go use this dragging force here to derive for our differential equation. So the next step is, since we already identified the forces that act on the body, so we're gonna go use the Newton's second law of motion, which is equal to the sum of all forces that act on the body is equal to m, or the mass of the object that's moving, and its acceleration. How much does this object accelerate? Okay, but you remember that in calculus, A is just equal to the instantaneous change of velocity per instantaneous change of time. So that's dv over dt, right? So acceleration is dv over dt. So we can actually make this summation of F, or the sum of all forces that act on a body, is equal to mass times dv over dt. So this one here, since your body accelerates downward, so its movement is directed downward, and we treat this as positive. So we also treat this f of g, or no, I mean fg is positive, right? So sum of all the forces fg, which is mg, minus kv squared. So you just sum these forces. We've already put a negative sign before kv squared, so that would be okay. It's automatically like summed up using the negative sign. So that's equal to m dv over dt. So next is we divide both sides of the equation by m, so that will be mg over m. That will be left with g minus kv squared over m, right? Kv squared times 1 over m is equal to, you multiply this to here, m dv dt over m is just dv over dt. So now we already got our equation for our acceleration, or our for dv over dt. So we're gonna go check our answer. Is it correct? We have g minus kv squared over m. So that's correct. So now we've already determined the differential equation for the velocity v of the falling body of mass. So that's what we're looking for, right? dv over dt. So we found it and it was right. But I'm going to show you its graph, this one here. So we treat, we're going to graph this one in GeoGebra application. So dv over dt, we're going to go make it y. And v, we're going to go make it x. What, so that we're going to have y is equal to g minus k over mx squared. So we're gonna go input this one in GeoGebra, and I'm gonna show you the characteristic of this differential equation. And I'm gonna explain the phases, the free fall phases of this quadratic drag. So now as you can see, we have a function f here. Y is equal to, you remember our equation is y is equal to g. Our g is 9.81 minus k over m. So our k over m, we change it. We can change k, but we only put 1.1, maybe these 0.9 k, 0.7 k. This is what happens when we change the k. And m, the mass, we can also change, like from 22, that's in kilogram, 43 kilogram. We change it to 50. So as you can see, the graph also changes. So how does it change? How does your graph? So this parabolic graph here is actually the graph of your dv over dt, or your acceleration, right? Acceleration is just equal to, or dv over dt is just equal to 9.81, which is the g, minus k over m x squared. So what happens if we increase our m? What happens to our dragging force? So let's go study this graph. We will set k as 1, and we will set m as, like, say 60. Just go 60. Let's go set our k as 1 and set our m as 60. Okay, that's just like approximately equal to 60. So say that is the value of k is 1 and the value of m is just 60. So this is your graph. This is your equation for your dv over dt, or your acceleration. This is dv over dt is equal to g minus k over m x squared. So this is a parabolic graph which opens downward. At the initial jump, the skydiver has, so that's a free fall body. That means its initial velocity is equal to 0. So if your initial velocity is 0, that means your acceleration is just 9.81. And as you go down, as the skydiver go down, this one here, the y-axis is the acceleration, and the x-axis is the velocity. So we only let the acceleration be the y-axis, and we let the velocity be the x-axis. So at the start, where initial velocity, as the body free falls, its velocity is equal to 0. So that means the acceleration is 9.81. And as it like moves down, as the skydiver falls down, the acceleration actually reduces. And this one here, as velocity changes, so as the dragging force. So as you can notice that the dragging force is directly proportional to the square of the velocity. So the velocity itself of the falling body contributes to the dragging force. So as you move here, you increase your velocity, so as your drag force, so as your air resistance. In fact, it's even directly proportional to the square of the velocity, the dragging force. So that means your 9.81 actually reduces. That is reducing. So the acceleration gradually decreases as your dragging force, which is k v squared, also increases. So you increase your speed, you reduce your acceleration. That's why it's going down, the acceleration, as you increase your velocity, because the dragging force also affects the acceleration. And your body will reach a point where its acceleration will equal to 0, right? This one here, your y-axis is the acceleration, and the acceleration reaches 0 at a certain velocity. So this velocity here, we call it our terminal velocity. Our terminal velocity is when your acceleration becomes 0. That means your mg, the body of the falling object, like the weight of the fallen object, equals to the dragging force. So we're going to go derive that and how we're going to find the terminal velocity. So you just remember, during terminal velocity, the drag force matches gravity. that's equal to, that's mg is equal to kv squared, because your acceleration becomes 0. So you just equate dv over dt is equal to 0, and you're gonna go get the terminal velocity if you solve for v. So the net force becomes 0, so the acceleration stops during this time. And from that, the skydiver will fall at constant velocity, which is the terminal velocity. So we're gonna go derive that terminal velocity. So now that I've shown you the graph of dv over dt, we'll let dv over dt be just equal to y axis. We make this our y axis, and v, we also make this our x axis, right? And the graph actually is like this, a parabolic graph which opens downward. So that's dv over dt, and our x is just the velocity. Our y is acceleration and our x is the velocity. So you've seen the properties of the acceleration of the body of the fallen object, right? So now we're going to go solve for the terminal velocity. As I've told you earlier, the terminal velocity is when the acceleration becomes 0 and where the net force becomes 0 as well, because the acceleration is now 0 and the acceleration stops. So it stops accelerating, so it just keeps on moving at constant velocity. So we equate this one to 0. So our dv over dt becomes 0. That is 0 is equal to, we copy this one, g minus kv squared over m. But now to identify that vt, we denote the terminal velocity as vt to identify that this one is the terminal velocity. So we're going to go solve for our terminal velocity. We multiply both sides of the equation by m. 0 times m is 0. G times m is just mg minus kvt squared. So that's like mg, add kvt squared to both sides of the equation. So now we have mg, that's 0, is equal to kvt squared. We divide both sides of the equation by k. We have mj over k, I mean, is equal to, cancel these one, we have vt squared. So take the square root of both sides. We now have our terminal velocity as square root of mj over k. So this terminal velocity, which is equal to the square root of mj over k, after your falling body reaches that certain velocity, it will only keep on falling with that velocity. So velocity will be constant and it won't be accelerating. Okay, there will come a point that your falling object will reach that terminal velocity where it's not accelerating and it will keep on moving to that certain velocity. So basically we have an equation of our acceleration, which is dv over dt is equal to g minus k over m v squared, right? So we already found the answer and we are correct. And I've also discussed about the terminal velocity which we got, and in the next video we're gonna go look for the v of t, the velocity of the object in terms of time. We're gonna go look for it using this differential equation here, this first order nonlinear differential equation. We're gonna go use it to solve for v of t, but I'm gonna do it in the next video, and we're gonna also express v of t in terms of vt. We're gonna use this differential equation and we're gonna go express our answer in terms of VT also and in terms of MJ and K. Okay, that's all for now. And I'm gonna look for my other video which solve for V of T.